Today, I will present joint work with Sheila McIlraith on learning interpretable models expressed in linear temporal logic. This work had been presented at ICAPS 2019. We are interested in learning human interpretable models that explain observed behavior. Such systems can be used for learning the rules of chess, or learning what's the recipe of cooking pasta, or learning what's a logical specification for a sequential circuit. We want to learn models that are human interpretable, and that's why we chose to use linear temporal logic on finite traces as a modeling language. LTLF extends propositional logic with temporal operators, next, until, always, eventually, and others, whose semantics are very similar to what they mean in English. That's why LTLF is human interpretable. With LTLF, we can express behaviors such as boil pasta until it is al dente and next dry the pasta. We study two paradigms of model learning, passive learning and active learning. In passive learning, the objective is to learn an LTLF formula that is consistent with a set of positive and negative examples. And here, by examples, we mean finite length sequences of states that showcase some behavior. In active learning, the learner interacts with an oracle by performing two types of queries. Membership queries ask whether the target model is satisfied by a certain example. The oracle can answer yes or no. Equivalence queries ask whether the target model is equivalent to a certain LTLF formula. If the oracle answers yes, then we are done. We have learned the model. Otherwise, the oracle responds with a counterexample. Our approach works as follows. We start with a set of positive and negative examples. From those, we learn an automaton that accepts all the positive examples and rejects all the negative examples. From this automaton, we will be able to automatically extract an LTLF formula that will be the model that we want to learn. Our system has a number of applications because the learned LTLF model can be used as a specification for LTLF synthesis, LTLF planning, as a reward function for MDP planning and reinforcement learning, for inverse RL, and other applications. So we mentioned that we are going to learn automata, in particular alternating finite state automata. An AFA can be thought as a tree. And what we see here are different subtrees that are skeletons, each one associated with a different subformula. So what we see here is a skeleton for the formula alpha and beta, and skeleton for the formula alpha or beta, and skeleton for the formula eventually alpha, etc. And what these skeletons do is to represent three expansions. So here, let's say that we are processing an state trace at a certain point in time. So what this skeleton says is that we have to expand the two branches, the one for alpha and the one for beta. This skeleton says that we have to expand one of the two branches, and we are free to choose either alpha or beta. This skeleton for eventually alpha says that we can choose to expand the branch for alpha, or to choose to expand the other branch, advance one time step, that's what the white circle says, and then loop back, and so forth and so on. So these skeletons can be composed together, and they define a set of three expansions. So alternating automata are useful because these three expansions can be used to decide whether a given state trace satisfies or not a given LTLF formula. So this state trace satisfies a formula if there exists one tree expansion that finishes in nodes that are accepting. And accepting nodes are those that are marked here with double circles. Okay, so how can we use SAT to learn LTLF formulas? Let's see it with an example. So we have only one positive example here, E, that is P and then Q. And let's say that the target LTLF formula is P and next Q. So the learner doesn't know what is this formula. We want to learn it. So how does it work? The SAT solver has certain slots, 1, 2, 3, 4 in this case, that has to fill in with either literals or connectives or temporal operators. And we also have clauses. These clauses capture the tree structure of the skeletons that we saw in the previous slide. And so now the SAT solver has to choose branches or tree expansions in these skeletons to ensure that there's some tree expansion that is accepting. Okay, so that's how it works for positive examples, but there might also be negative examples, and we want to make sure that the automaton rejects the negative examples. So how can we do it? There's a naive way of doing it, which is by enforcing that all the tree expansions are rejecting. That's a bad idea, because we need to check a very, very large, potentially, number of expansions. There's a much clever way of doing it, which is reasoning on the dual of the automaton. So what's the dual of the automaton? The dual of the automaton is another automaton that accepts the complement language. So this way we have to enforce that the dual automaton has some accepting tree expansion on the negative examples. The good news is that the dual automaton is very easy to compute. It can be computed on the fly. In fact, it doesn't require any computation at all. It only requires to dualize all the operators so that the ands become ors, the untils become releases, and so on. So the next question that we answer is, what is the sample complexity? How many examples do we need to make sure that we are able to learn a certain LTLF formula? And the number of examples that we need is exponential in the size of the target formula. So this exponential is kind of a lot. It seems very large. But the good news is that the alternative, which is learning deterministic finite state automata, requires a double exponential number of examples. In contrast, we require a single exponential, which is exponentially lower. Next, we did some experiments, and we have seen that learning simple LTLF formula require a very low number of examples, like around 10. In contrast, learning DFAs requires like up to 4 times more, up to 40 examples. And on top of that, the DFAs, even though they are relatively small with 4 and 3 states, they have a large number of edges, which means that they are not really human interpretable. In contrast, the formulas that we learned are very small and they are very easy to be interpreted by a human. Next thing that we tested is active learning. So we saw that learning formulas of size up to 8 is quite easy. It requires less than 1 second of runtime and under 20 examples. In contrast, learning formulas of size larger than 9 makes it more challenging for our system. And the last thing I want to show you regarding the experiments is a very cool application of our system, which is learning behavior classifiers. So now what we have are, let's say, different agents that are behaving differently, and we want to find or learn an LTLF formula that discriminates between the target behavior and other behaviors. We did that with our system, and it required only 0.1 seconds to learn a classifier with just a few examples. In contrast, an LSTM required 16 seconds, which is 2 orders of magnitude more time. with the extra thing that our system is human interpretable, whether the LSTM is just a black box. In summary, we introduced a novel mechanism to do passive and active learning of LTLF formulae. We conveyed that we need up to an exponential number of examples to learn these formulas, which is exponentially lower than the bounds for learning DFA. And our mechanism can be used in conjunction with many other systems for LTLF planning and reactive synthesis, reinforcement learning, inverse RL, plant recognition, behavioral classification, and other applications. With this, I conclude my presentation. Thank you very much for listening, and I'm very happy to answer your questions.